Okay, welcome everyone, and good afternoon, and welcome to this talk about toward multi-tenancy support from HDFS. My name is Xiaoyu Yao. I'm a software engineer working in HDFS team at Hortonworks, and also I'm a Hadoop committer and a PMC member. This talk is mainly to help understanding of multi-tenancy support from Hadoop and the HDFS. And also, we will talk some of the ongoing work for better resource management that we're doing right now. And the agenda of today's talk will first have an overview of the multi-tenancy and requirements. And then we will go over the Hadoop multi-tenancy features from HDFS, Yarn, and some of the upstream projects. And we will focus on the HDFS resource management and the multi-tenancy offers. The fourth thing we will talk about is the resource management, where the resource coupon. And at the end, if we have time, we'll pick up some questions. And with Hadoop has become more and more important for enterprise, and the size of the cluster has grown significantly, and more small cluster has been consolidated into a large cluster, so that to improve the efficiency of the cluster operations. Also, this centralized managed infrastructure can lower the total cost of ownership and also simplify the management of the cluster resources. It avoids the resource underutilization and to improve the overall efficiency of the operations. So for a multi-tenant Hadoop cluster, the basic requirement we categorize as three pillars. The first and the most important is for resource sharing. And with resource sharing, you can put all kinds of different workloads, such as batching and streaming, and also some of the low latency workloads and all sorts of workloads they can run within the same cluster. And to making sure the different workloads won't in fact affecting each other, it's very important to keep certain level of resource isolations, either physical or logically, so that to meet some of the regulatory requirements and also some of the performance requirement for some of the applications. And to meet this some performance requirement, it's also very important to have resource management to making sure the resource assignment and allocations meet the performance goals of different applications. And here, some of a simple summary of some of the multi-tenancy related features from HDFS, Yarn, and HBase. From HBase, they have all of those three layers. They have the resource sharing features because it's a distributed system. It's designed to be shared and to use the distributed resources efficiently. And from resource isolation perspective, HBase support namespace in recent releases, and you can group a bunch of tables under the same namespace and manage those tables within the namespace. And it also supports resource management where the quota. So you can basically set limit the number of tables within the namespace. You can limit the number of region servers that can be used for some namespaces. And also you can group the region servers into a regional server group. That's another very important feature to support the resource isolations of the tables. And from Yarn is the is the central of the resource manager for the Hadoop clusters. It basically has a lot of features related to resource isolations. For example, you can use the queue is the basic scheduling unit for the resource management, and you can assign different weight of resource usage for the queues, and the jobs will be assigned to the queue based on its priorities. And the node label is another feature added to Yarn as well to excuse me, to isolate the load so that you can basically partition the cluster based on not only the organization but also on the hardware, software requirement of the jobs, and also the workload type of the jobs. And from the resource management perspective, you can use the capacity schedulers assign different weight on the queues. And HDFS is the bottom layer of the Hadoop stack. It provides robust and scalable storage for all kinds of workloads. And the federation is a very important feature to guarantee the resource isolation because traditionally HDFS is just a single name node and a bunch of data nodes working together to provide a consistent global space for almost unlimited amount of storage for upper layer MapReduce jobs and HBase and all the other upstream projects. And we have a bunch of resource management related features such as quota, fair calcul, and backup. We'll talk about that in later slides. And HDFS resources, before we talk about the resource management, and we talk about the HDFS resources. And HDFS resources reside in two parts, the name node part and date node part. On the name node, it basically manages the metadata of the file system. And under the same global namespace, and you can have the amount of files, directories, and that's what we call the capacity of the name node. And also you can have the storage space available to store the data blocks for the files under the namespace. And the storage type is another feature we added to embrace the new hardware, such as memory-based computations and RAM, which maps to the RAM disk storage type. And we also have the SSD for low latency accesses of the IO, low latency IOs. And also we have the disk and the archival storage for long-term low-cost storage of the code data. And with storage policy, you can specify the capacity usage of the directories for the jobs and for different jobs of different users. And the other category of resources, what we call the runtime or operational resources. This is more related to operate the cluster, where on the name node side you have basically a RPC server running on the back end and listening for the client requests from different RPC clients. And there are limited number of RPC handler threads. So if you have large amount of users sending the metadata operations to the name node, and we want to making sure those resources are managed wisely, rather than all the resources overwhelming the name node, and the name node end up with an unresponsive state, and which won't be able to survive this kind of overwhelming situations. And for the data node, it's basically serve the blocks for the files, and we have the disk and network resources as a basic resource unit to be managed. And as I mentioned earlier, the federation is a very important feature to guarantee the isolations. So from previous single global namespace, we now have multiple names. We now can have multiple name servers running simultaneously. Each one hold part of the namespace and serve part of the request toward those specific namespace. And an important abstraction layer is the block pool. The block pool serve and the namespace is a one-to-one mapping. And the block pool is a collection of blocks that are deployed across all the shared data nodes. And we can see below the block pool, one can have their data blocks replicated across all the data nodes, and the other block pools can also be using the same set of data nodes. And this is a typical multi-tenancy environment. You can have, for example, some of the finance department, they can save their data on the name service one, and well, you can have some research and development data saved on the name service, other name service servers. so that they are physically isolated name nodes, and they won't affect each other. If you restart one of the name node, the other name service won't be impacted by other users. And from the capacity management perspective, HDFS, like many other upstream projects, has provided quota management from even the Hadoop version 1. So the namespace quota is one we support to limit the number of files and directory that can be saved into the name node. And the storage space, just like the limit the number of blocks you can save into the HDFS cluster overall. And HDFS 75884 add additional support for the quota by story type. And this limited the amount of usage for some of the precious hardware, like you want to limit the usage of your RAM disk resources for certain directories, and you want to limit the SSD usage only for certain kind of workload, such as like HBase. You don't want to use your SSD for MapReduce jobs, and that can be limited by this quota by storage features. And there are some limitations with quota because it is kind of static configured by the admin, and it's only set up on a per directory based. So if you want to limit the quota usage for a single user or for a single job, there is no easy way to do this. You can either set up a mapping of the directory to the users, but with the multi-tenancy scenarios, you have a lot of users, and it's really a big management overhead to establish this kind of mapping between the directory and the users. And on the name node side, the resource management is more about the runtime resource management, and the name node is here we look at the typical name node implementation. So there's a HDFS client running as RPC client, talk to the name node. And on the name node side, usually there's a listener thread accept the client request. And once the RPC is accepted, the header is decoded by the reader thread and put it into the RPC call queue. And the call queue just queue up the request and waiting to be served by one of the handler thread. And the handler thread is the actual thread that implements the file system operations, and which on the back end is the file system namespace for corresponding method implementations. And there are two categories of RPC requests. So one category is what we call the internal RPC. It's used to manage, for example, the data node membership and the block report. And those are usually the RPC from data node toward the name node. And there's other kind of RPC, which is for the HDFS high availability features. And the Zookeeper failover controller is the component that used to detect the name node liveness. And when the name node doesn't all respond to the ZKFC for a certain threshold, the ZKFC will kill the name node and do the automatic failover for the high availability use scenarios. And the other kind of RPC is what we call the external RPC. This is probably most of the application developers be familiar with is the HDFS or the distributed file system APIs, where the client requests the file system metadata informations from name node to get block information to create, delete files, or list the directories, and before. So all these RPC requests until recently they are sharing the same RPC call queues. And what the problem with this is the RPC accesses from certain jobs can be impacted by some offending jobs. For example, there is a job sending thousands of requests per second toward the name node, while the other job just need a few requests per second toward name node. And when they share in the same call queue, and even those less offensive jobs, they get a significant delay because of those offending jobs. And also, there are cases we have seen in the field where the internal RPC get impacted by the external RPCs, and some of the internal RPC also can impact each other because sometimes like the inefficient block reporting implementations can cause significant delay on the server side, and then the external RPC can get delayed as well. And there could be like one blocking RPC method implementation that will prevent all the other calls from being returned timely. And to protect the HDFS internal RPCs, there are a few improvements since Hadoop 2.6. And one of the important improvement is we have added a dedicated service RPC server for the internal RPCs between the data node and the name node for block report and heartbeat, so that those important maintenance RPC won't be blocked due to some of the client RPCs or other RPC requests. And the problem with this is when the data node does not report heartbeat to the name node for extended period of time, those data nodes will be treated as stale or dead, and then this causes a very expensive re-replication of the blocks across the data node. And those cause unnecessary network bandwidth and the resource usage. And this dedicated service RPC helps a lot in these kind of situations. And the other improvement is we added the dedicated Lifeline RPC server and the corresponding port, so that this protects for the HDFS HA scenarios, the Zookeeper failover controller and live detectness traffic won't be affected by for example, the internal service RPC and the external client RPCs. And this will ensure there isn't any unexpected failover due to those kind of delays of the RPC processing on the server side, because they are sharing the same call queues. And with these two dedicated service RPC and Lifeline RPC port, all the external RPC will still go to the default client port, and typically like 2080. And the call queue is playing a very important role in the multi-tenancy environment, because there could be more intensive accesses than traditionally you have a dedicated call queue for one certain type of workload. And a good call queue should behave certain good attributes. For example, there won't be a lot of call bloats in most of the cases. And even there are some spikes from the calls, there shouldn't be just like should be just a temporary increase in the queuing delay, and then the call queue will be quickly consumed by the servers, and so that the server will keep a constant departure for the calls arrive the system. And for a bad call queue, will experience something on the other side, like it will experience some call bloat and extended delays upon some of the bursts, and the delay will keep increasing, and this will cause low utilizations and high queuing latencies on the server side. And Hadoop 9641 is an important feature that introduced multi-level call queues to replace the traditional single-level linked block call queue that serve all the requests. And with the dedicated service RPC and liveness RPCs, and the client RPC will all go to the same call queue, there is still a chance a single offending job can monopoly use all the call queue resources. And this fair call queue address the problem by separating those traffic from different clients. And the different queues assigned with different priority levels based on the caller history and the amount of volumes that has been sent out from that client in the previous time window. And the higher priority will be assigned to those callers that use the call queue resource fairly, and those users who send out extremely high load into the name node, trying to overuse of the name node resources will be penalized by putting into the low priority call queues with slower processing on the server side. And with the fair call queue, and what would happen if the call queue get filled up? And the behavior is without Hadoop 10597, and the call queue will get filled up with calls, and all the subsequent calls coming into the system will be blocked and eventually time out and fail the request. And this can be very expensive because the client, once it failed the request, it will retry, and then the call queue will keep into the bloated states, and the name node won't be able to recover quickly from that state. And what the Hadoop, what this backup feature added is basically a name node RPC throttling. It will back off those clients and tell those clients to do the exponential backoff and to send out the request later rather than just retry immediately, so that to help the name node to recover from the overload situations. And another improvement over the Hadoop RPC, name node RPC throttling is what we added is the backoff based on the response time. So we add a response time threshold onto each of those different priorities. So some high priority call queues can be assigned with a lower response time expectations. And once those expectations is not met, we can trigger the backoff of the low priority calls, so that to guarantee the high priority the calls from the high priority call queue will always get closer to their expected performance goals. And we also add a few call queue and per user and per queue metrics to better understanding the call queue behavior. For example, we can now get the response time, average response time from each of the call queues, and these metrics can be plotted and to monitoring the status of the service at the name node side. And to this name node RPC throttling, also we have the improvement over the scheduler interface. Previously from fair call queue, the scheduler, the sub queues, and the multiplexers, they are combined in a single unit. So you can switch between either the fair call queue or the linked block queue, and there is no easy way you can tweak the scheduler interface. The scheduler is the component that assigns a priority for the call queues. And with the abstraction, we can now have a flexible priority assignment logic sharing the same call queue and the multiplexer infrastructure. So, for example, without the fair call queue, you can basically use the default RPC scheduler, which assigns the same priority for all the calls. You can also use the decayed RPC scheduler as part of the fair call queue, which assigns the priority based on the previous call volumes of different users. And you can also have some experimental schedulers, such as configurable list of users that will always be assigned high priority, and other list of users that can be assigned for medium priority and others for low priority, for example, for the batching jobs. And the throttling is only part of the resource management. And the end goal of the resource management is to have some sort of guarantee for the performance. And the QoS is one of the features we want to look at. And one of the Hadoop JIRAs that caught our attention is Hadoop 9194. It's basically add a QoS field into the RPC headers. It allows different mechanisms to set the QoS levels for your RPC calls. And even though it doesn't have any concrete implementation yet, but it has the RPC layer mechanism to support potential QoS layer improvement in the future. And with the QoS in the man, we look at other layers in the Hadoop stack. Yarn is as we all know, is the conceptual resource manager for the Hadoop cluster. And it currently have a well-designed model for the CPU, memory, and the GPU resources. But for the HDFS resources, it's out of the management for Yarn. So that could cause some problem. For example, the priority inversion is one of those. A high-priority Yarn job can send a lot of RPC requests into the name node, and those requests can be put into the low-priority call queues, and which is contrary to the priority assignment from the job submission. And the other case we have seen is it's really hard to identify and manage the bad callers. And with fair call queue, some of the users are well-defined, while others maybe not. And some of the queries or workflow jobs, they all share the same users. So some of the good users can be the victim of the bad users because they are sharing the same user identities. And if one of the jobs or one of the queries that is not well designed, it's sending overwhelming amount of RPC requests toward the HDFS name node, and then the fair call queue can put all the RPC requests from the same user into the low priority call queues, and to be processed, to have less probability of being processed by the handler thread. And also, even with fair call queue, there is no guarantee for the differentiations. So so the decayed RPC scheduler will decay the call count. So eventually, even intensive callers maybe come back and surface as high priority users. And on the data node side, at the I/O bandwidth, currently there is no differentiation for the reader and the writer I/Os, and those including the disk and network. And the data node currently supports some static throttling for the HDFS balancers, but there is no throttling on the regular replication traffic for the read and write request. And we have proposed to use the resource coupon for better resource management integration with Yarn-based resource management models. And the key to the resource reservation is we propose a new concept called resource coupon. The coupon is designed to move us from the throttling model to the management model, and it's basically give you final control of the resource usage rather than just simply say you are not allowed to use, you should be back off. We now have a predefined amount of resource usage for your workload, for your jobs, and so that Yarn, when the job is submitted, it can request the amount of, for example, HDFS name node resources desired to use. And once it's granted, it will be guaranteed to have that amount of name node RPC resources to be used. And to many aspects, the resource coupon looks like the delegation token, but the difference is it will work for both Kerberos and non-Kerberos clusters, because the delegation token can only retrieve from the Kerberos security channels, and we want to work both Kerberos and non-Kerberos situations. The security is guaranteed by only allow the privileged service user to request the resource coupons, such as HBase service users or the Yarn service principals to request the resource coupons on behalf of the users who submit the request. This is different from the delegation token, where the user can request the delegation token directly from the name node. And the coupons can also be serialized and deserialized for use with the container and the tasks. This is similar to the delegation token as well. And the coupon also can be renewed for a long-running process, and it can also be canceled once the intended job is finished. And for each of the resource coupons, we define the resource coupon identifier, including both the final of the owners, such as the never-reduced jobs, or the have query IDs to help identify and manage the good user, both good user and the bad users. And we don't want to mix with users. The user can be a very broad name under which a lot of jobs are running under the same. And the resource type, we have reserved the name node RPC resources and the date node IO bandwidth resources as the resource type. And each coupon will have its intended resource types. And it also have the flexible management unit for different resources. For example, you can specify the maximum or minimum percentage of the resources available for such as name node RPCs. You can also specify absolute values, for example, the date node IO bandwidth. And the new component that be responsible for the resource coupon is what we call the resource coupon manager. It will grant, renew, or cancel the resource coupons on behalf of the name node. And it also monitor and report the usage of the resource coupon. And upon each of the RPC requests, it will check and validate the resource usage request. Overuse will be back off with resource coupon violations. And to be compatible with some of the existing applications, what we call legacy applications, without resource coupon, we carve the HDFS resource name node RPC reports into two separate pools. The fairness pool is used for those legacy applications which won't send resource coupons along with their RPC request. And the other resource pool we propose to have the managed pool, and the managed pool will be used for those RPC requests that are sent out to name node with resource coupons. And those resource coupons will be either honored, either granted or denied when the job is submitted. So this is a simple example of how the coupon work with Yarn integrations. Say you have a client that want to submit a job to the Yarn resource manager, and the resource manager then will request a coupon from name node for the desired amount of name node RPC resource usage. And if the resource coupon manager granted the coupon can be serialized and sent out to the Yarn node manager. And node manager, when it starts the containers, and the job can send RPC requests to the name node to request, for example, get the block information, create, delete files on the HDFS namespace, and the resource coupon will be attached to the RPC request. And those requests will be checked by the resource coupon manager, and to ensure the granted amount of resource usage can be used. Overuse will be rejected. On the name node side, we also want to have better control of the resource usage. For example, we want if we don't have this name node resource management, client can write too fast into the date node, and this can overload the date node and making the date node unresponsive. And when the write happens, when this situation happens, the client can fail the write pipeline and invoke the write pipeline recovery, which is very expensive. And there are quite a few community JIRAs proposed to have a static I/O throttling, but most of those are not mixed through the discussion process because there are a lot of concerns around having a static configurations is really hard to tune in the heterogeneous cluster, and some of the, especially for the multi-tenancy clusters, and it's really hard to get a magic number to configure this for users of and also there's one I/O throttling on the data node that does make into reach the agreement on the community. It's the HDFS 7270, which add congestion signal capabilities to indicating the write pipeline is overloaded, and the ECN can be sent back to the DFS client to indicate the server status, and the client can then do the backoff and to reduce the load on the data node. And some of the future work we want to extend the resource coupon model to reserve the I/O bandwidth for on a per job or for query basis, so that it can be final control of the resource usage to guarantee the level of service from overall the HDFS. And I think that's pretty much it. And I have 5 minutes. And if you have any questions, I can take it. Yes.
I've seen problems where if the name node is too busy processing a lot of RPC requests, it becomes a little unresponsive on the HTTP port. Have you seen this issue before? Because we use the monitoring curl organization TP port, so it takes a long time when the name node is busy to respond to those requests.
Yes, the question is the name node become too busy and it takes a very long time to respond to the RPC request. Yes, we do see some customer cases where the name node get too busy to handle the request, and that's why we have a lot of improvement on how we isolate the name node traffic, because the RPC, when you mix them together, it's really hard to manage the RPC traffic. And now that we have the service RPC, we have the lifeline RPC, so that all the client RPC are dedicated into that specific port, and then you can have a clear mapping of the users who is overloading the name node.
Sorry, I was talking about the HTTP port.
Which one?
The HTTP port on the name node.
Oh, you mean the web HDFS, or?
Well, the port included in the name node, to get metrics.
Oh, the UI port of the name node. Yeah, I think that's a different issue. So when the name node get too busy, the question is, when the name node get too busy, even the HTTP port won't be able to respond to the request. Is that the question? Yeah, I think there could be some locking issues on the name node side, and there are some community JIRAs that are working on to reduce the big global lock on the name node side, and but this is separate from the RPC call queue, and yes.
Federated name nodes, two questions probably. Are the block pools, are they virtual? Meaning, can I have a block that appears in two different pools? Or that appears in two different name nodes in the same block? And the second question is, me as a client, do I have to specifically say which name node I'm connecting to? And what happens if I need a data set that appears in two different name nodes?
Yeah, so the question, the first question is the block, whether the block can be shared across the block pools, and the answer is the block won't be able to share it across the block pool. Each one is a separate entity, so they won't share the blocks. And the second question is how do you access across the different name nodes? And there are some community JIRAs and to handle this problem. So the early discussion is like have a big global namespace that covers all those sub namespaces, and so that you can easily resort to those global namespace and look them up separately. And but there is no actual it hasn't been materialized yet, and there are other direct discussions. Like for example, you can let the client mount the federated file system into a separate like the ViewFS. You can mount them to different mount point, and you can copy that over, but you won't be able to do some certain operations. For example, rename. You cannot rename the files efficiently for some of the workload, like you want to do the ETL, you want to move the data across different namespace. This is not doable as of now. Yes.
From which HTTP version we have a different RPC rule for internal and external RPC?
I believe it's HTTP 2.3.
From an admin perspective, is there any configuration we can say that we can define this much resources for our internal and the other hostess for external? Like how we are defining the queue for Yarn, is there any config file we can do so? By doing so, we can just throttle the RPC calls between internal and external?
Uh, Actually, there are some configurations, and we have some documentation around how you can effectively protect your name nodes, and I can share that later offline. And basically, there are configuration for dedicated service port and lifeline port and a client port. And the client port is well known because it's by default you have already set it up. The service port and the lifeline port is something new. You have to configure that separately. And for the HA setup, you also need to reformat the Zookeeper, the ZKFC, and there are some additional configuration steps. But once it's a one-time thing, once you have set up, and you don't need to additional configurations. Yes.
So what's the best way to go about identifying the RPC traffic?
And we, this is the question is how to identify do you mean the callers of the RPCs or the RPC traffic?
Yeah, so if my name nodes are constantly having a huge amount of RPC traffic, and I want to find out what's generating that traffic, how would I go about doing that?
Yeah, I think there's a talk yesterday from my colleagues, Chris and Arpit, and they mentioned there's a tool called NNTop, and the NNTop basically is a metric you can inspect in the previous time window. For example, 6 minutes, 1 minute, 5 minutes, and 15 minutes. You can get the top users who send the most amount of file system requests. And there are also additional metrics we added from the scheduler. So the scheduler has all the caller information because it used the caller information as part of the scheduling the priority assignment. So the more you put into the name node, and the lower the priority you will be assigned. And those are exposed as the JMX and also the metrics as part of it. So if you search the name node RPC JMX, you can easily find the default RPC, the decade RPC scheduler. It has the number of RPC calls made by the users, and it directly match the priority levels that is assigned to the corresponding call in the future. Yes.
Is there any development regarding native HDFS replication across clusters?
Can you repeat your question?
Yeah, is there any development regarding native HDFS replication across clusters? So if you want to configure on an HDFS level that one cluster HDFS data should be replicated to another cluster?
You mean replication across cluster? You mean for the disaster recovery scenarios, or something similar, or backup? I think there are some community jurors that are working on this to making, for example, DSCP tools more efficient for those kind of disaster recovery scenarios. And beyond that, I don't know the status for that. Go ahead.
Since you have this more logic in the RPC scheduler now, in like a real kind of production system with a lot of users, what's the like memory and CPU overhead on just running that scheduler? You know, maintaining the state about how many queries each user is submitted, et cetera.
Yeah, that's a good question. And the question is the CPU and the memory usage of maintaining a complex scheduler for better control of the resources. Yes, the scheduler has to maintain for example, in the file call queue, you have to maintain a caller count of individual users. If you have a lot of users, it can be a huge map of the users corresponding caller count. And in this case, for the resource coupons, you have to maintain the state of the coupons. And the good thing with the resource coupon is it can be it will be canceled once the job is done. And if you it's not intended for something you have to always keep. And so once the job is done, the resource coupon will be cleaned up, and we don't expect a lot of runtime overhead for the coupon-based management. Yeah, the feature itself is still under development, so we don't have the data for that yet. But we will definitely consider the overhead, and we'll have some performance numbers on that in the future. Yes. Yes, I think that's it. If you have any further questions, we can talk offline.